Hello everyone. Today I am going to present experiment number 3, sampling, aliasing and reconstruction from digital communications laboratory. I have implement this experiment using Python in Google Colab, mainly using NumPy and Matplotlib. The main purpose of this experiment is to understand the sampling theorem, observe aliasing and reconstruct the sampling signal using sync interpolation. This experiment follows a complete process. First I generate a two-tone signal, then I physically sample it at different sampling frequency. After sampling, I perform sync reconstruction. Finally, I calculate the reconstruction error, compare the signal in the frequency domain and calculate the aliased frequency for the undersampled case. Here, the main objective are to verify the sampling theorem using a two-tone signal and to test three different cases: sampling above, at and below the Nyquist rate. I also compare the original sampled and reconstructed signal, calculate MSE and RMSE and identify the aliased frequency when the sampling frequency is below the Nyquist rate. And the theory portion. Now coming to the theory portion, here the reference signal xt is equal to sine of 2 pi f1t plus 0.5 sine of 2 pi f2t. Here f1 is equal to 50 Hz and f2 is equal to 120 Hz. The physical sampling is represented as xn equals to x of nts, where ts is the sampling interval and ts is equal to 1 by fs. After obtaining the sample, I use sync interpolation to reconstruct the signal. Here is the condition. Here is the Nyquist condition. Fs is greater than or equals to 2 into Fmax. Here Fmax is 120 Hz, so that Nyquist rate is 240 Hz. The three sampling frequency selected are therefore 400 Hz, 240 Hz and 180 Hz. And the sampling interval Ts is equal to 1 by Fs. I also calculate the reconstruction error as the difference between the original and the reconstructed signal. The next is a system block diagram. First, the continuous two-tone signal is generated. Then it goes through the physical sampler and produce the samples xn. These samples are passed to the sync interpolator to obtain the reconstruct signal. And finally, I compare the reference and reconstruct signal, calculate the error and compare their spectra. Here three physical sampling rates are 400 Hz, 240 Hz and 180 Hz. Here is the algorithm of flowchart. The algorithm starts by defining the two frequencies, durations and plotting resolutions. Then I generate the reference signals and calculate the maximum frequency and Nyquist rate. Next, I select the 3 sampling frequency, generate the physical samples, and apply sync interpolation. After reconstruction, I calculate the error, the MSE value and the RMSE value, generate the time and frequency domain plot, and finally calculate the aliased frequency. This one is code part. Here I define the two signal of frequency 50 Hz and 120 Hz, and the duration of time is 0.1 second. I use a plotting resolutions of 10 kHz. Again, this is only the numerical resolutions for representing the continuous time waveform and is not the actual sampling rate. Here this function, sampling function, performs the actual physical sampling. For a given sampling frequency, it creates the sampling instant using Ts equal to 1 by Fs and calculate the signal values at those instant. This is the code of sampling function. You can also see that. And the next part is sync interpolation. Here I implement sync reconstruction. Each sample is multiplied by a shifted sync function, and all these shifted sync functions are added together. This gives the reconstructed continuous time wave. Next portion of this code is spectrum function. Here I use the FFT, fast Fourier transform, to obtain the frequency domain representation. The magnitude spectrum is calculated and only the positive frequency part is used for comparison. And simulate all 3 sampling cases. Here is the code. And here is the time domain plot. And here is the time domain plot code. Now we can do the time domain plot. Here is the reconstruction error code. Here the program loops through all 3 sampling cases. For each case, it generates the physical samples, reconstruct the signal using sync interpolation, and calculate the reconstruction error. Then MSE and RMSE are calculated and stored for comparison. Here is the code. And this part is reconstruction error. This graph show the reconstruction error. For 400 Hz, the error is comparatively smaller. At 240 Hz, the error is more noticeable because we are exactly at the theoretical limit. At 180 Hz, the error becomes significantly larger because the Nyquist condition is violated and aliasing occurs. So these plots provides a direct numerical indications of this effect by sampling frequency. Code of frequency domain plot. Here is aliased frequency calculation. This is the most important calculation for undersampled case. The sampling frequency is 180 Hz and the signal component is 120 Hz. So the Aliased frequency is absolute value of 180 minus 120, which is equal to 60 Hz. Therefore, the original 120 Hz component appears as a 60 Hz component after sampling. This demonstrates the main effect of aliasing. The next, this is the error summary. Here the program print the MSE and RMSE for all three cases. These values provide a quantitative comparisons between the original and the reconstructed signals. Generally, when the sampling condition is violated, the reconstruction error becomes significantly larger. And last one is parameter table. This table summarizes the important parameters. Our two signals frequencies are 50 Hz and 120 Hz, and the maximum frequency we can see that 120 Hz. So the Nyquist rate is 240 Hz, and physical sampling frequencies are 400 Hz, 240 Hz and 180 Hz. The plotting resolution is 10 kHz, but again it is only a numerical representation and not the physical sampling rate. Here is the graph: time domain sampling and sync reconstruction. This page summarizes the three time domain cases. At 400 Hz, the samples are sufficiently dense and reconstruction is close to the original. And you can see that at 240 Hz frequency, the system operates at the theoretical boundary. And at 180 Hz, the samples are insufficient to uniquely represent the highest frequency component and resulting in aliasing. Here is the graph of reconstruction error. Here we can clearly see that the reconstruction error change with sampling frequency. The below Nyquist case has the most significant error because aliasing cannot be corrected simply by interpolation. This is an important point. Sync interpolation can reconstruct a properly sampled band limited signal, but it cannot recover information that has already been lost due to aliasing. And here is the frequency domain comparisons graph. The original signal contains components are 50 Hz and 120 Hz. For the below Nyquist case, the 120 Hz components become ambiguous and appears at the aliased frequency at 60 Hz. So both the time domain and frequency domain result support the sampling theorem analysis. Here is the graph. The first graph is above Nyquist, second graph is at Nyquist, and third graph is below Nyquist case. From the observation at 400 Hz, which is above 240 Hz, reconstruction is substantially faithful. At 240 Hz, we are exactly at the theoretical Nyquist boundary. At 180 Hz, which is below 240 Hz, undersampling occurs and the 120 Hz component falls into a lower apparent frequency. We can also see that lower sampling frequency means fewer physical samples per cycles, and the reconstruction error becomes larger when the Nyquist condition is violated. The next slide is interpretation and manual aliasing validations. This page gives the manual validations of aliasing. For Fs is equal to 180 Hz and F is equal to 120 Hz. F alias equals absolute value of 180 minus 120, which is equal to 60 Hz. Physically, this means that the 120 Hz component cannot be uniquely represented at a sampling rate of 180 Hz. So after sampling it appears as a 60 Hz component. Therefore the experiment confirmed that the sampling frequency should be at least twice the highest signal frequency to avoid aliasing. To conclude, the sampling theorem was verified using a two-tone signal whose maximum frequency is 120 Hz. The Nyquist rate was found to be 240 Hz at 400 Hz. The sampling is above Nyquist and reconstruction is substantially faithful. At 240 Hz we operate at the theoretical Nyquist boundary, and 180 Hz aliasing occurs, and the 120 Hz component appears at 60 Hz. The time domain plot, frequency domain plot, and sync reconstruction and the error analysis all provide evidence of this behavior. Therefore, in a practical digital communication system, we need to choose a sufficiently high physical sampling rate and use an appropriate anti-aliasing filter before sampling. Thank you. Here is the Viva question. You can also see that and read. Thank you, sir. Thank you, everyone.